Quantized energy is one really important concept that is really necessary to understand all this stuff that's going on within an atom. You should have had at least an introduction to quantized energy in your prep chem classes because we do talk about a little bit about the modern atomic theory and understanding photons and a little bit there. But just in case it's been a while, let's take a little bit of a review and make sure that we all understand what it is that we mean by quantized energy. Okay, so this is one of the most classic explanations of quantized energy possible. So basically, quantized energy is that we have like individual little packets of energy that can move around in an atom. So it means that like our atom has specific energy levels within it. It's basically the difference between a staircase and a slope. So if we didn't have quantized energy, it would be more like a slope. So if we've got this ball and this ball is an electron that's moving around inside the atom, all right, the ball can just roll. We can stop it anywhere by just putting up a barrier. But within an atom, things have to be done in specific energy packets because an atom is more like, it's not exactly like a set of stairs, and I'll explain this in a little bit, but it's more like a set of stairs in that there's specific distances between each energy level. And so it's an all or nothing thing. You know, if it takes 10 kilojoules of energy to go from energy level, X to energy level Y, and the atom only takes in 9 kilojoules of energy, you're not going to make the transition. And conversely, if you're at energy level Y and you want to drop back down to energy level X, you have to emit out all 10 kilojoules of energy. So it's like, I'm not going to do this in here. I don't have anything to do it, but in a normal live classroom, I illustrate this by jumping on a chair. All right. Can I hover in between the floor and the chair? No, I can't. I can only go all the way up on the chair or come all the way down from the chair. And that's the way this quantized energy works. Now, one of the things that has come out of this concept of quantized energy is what we call the Bohr model of the atom, where sometimes it's also called the planetary model because it gives us a visualization of these discrete energy levels within an atom. So we would have our nucleus, and then we'd have an energy level, and another energy level, and another energy level. All right, obviously not to scale. And so, you'd have an electron here, and then, it could make a transition all the way up, or maybe you have an electron here, and it can make a transition, down there. And so we like the Bohr model because it gives us a good visual to help understand that we have these discrete energy levels within an atom. However, electrons don't behave like planets. They're not in little orbits around the nucleus. They're bouncing around everywhere. They're a lot more unpredictable than the Bohr model would have us believe. But the Bohr model is still a good visual so that we understand that we move from one energy level by intaking energy, and we drop down to another energy level by giving off energy. And that's these photons, or these little packets of light that are emitted when our electrons are bouncing around. Okay? Now, when we look at this, if we are doing a transition between energy levels that are closer together, then we don't have very far to go. And so we take in an amount of energy, and when we drop back down, we're going to be emitting a low energy photon because we haven't gone very far. But if we go up higher and we drop back down lower, more energy involved with a longer transition, and so a high energy photon will be emitted. And again, it's discrete, all right? You can't go halfway in between. It's only all or nothing. My little electron can't go here. It can only go all the way, okay? Now, when I mentioned that it's almost like a staircase, here's the difference. As we get further away from the nucleus, the energy levels actually get closer and closer together. So a normal staircase, every stair is equidistant from the stair above it, and they're all the same. But within an atom, the energy levels in an atom are a little different because the further out we go, the closer together they get. So when I go from energy level 1 to energy level 2, that's the biggest transition. And then when I go from 2 to 3, they're closer together. 3 to 4, they're closer together. 4 to 5, they're closer together still. Okay. And so again, it's still like a staircase, but the quantum staircase gives us a better visual for the fact that in an atom, it's not all equidistant. The further we are from the nucleus, the closer together the energy levels are. Okay? And so when we talk about that quantum of energy, that's that smallest quantity of energy that can be emitted or absorbed in this electromagnetic radiation. And so that's our photon or our packet of light. So sometimes we call this, a photon. It's just that packet of light. Okay. And most of the time, we're dealing with a single quantum of energy. So when I look at these formulas and I just have, E equals h nu or E equals hc over lambda, and I don't include the n, we're just assuming we're dealing with one quantum of energy. And for the most part, that's what we are looking at. But if we were to be dealing with a larger quantum of energy, if we're dealing with more than one quantum of energy, then n is just the number of quanta of energy we're dealing with. So if we were dealing with 2 quanta, it would just be 2 times, h nu, etc. Okay? All right, so we're just going to practice again. Okay, so I've got a sodium lamp with a wavelength and a frequency. So what's the energy? Well, you could put it either way. We'll do the lambda. Okay. So minimum energy, so we're going to do 1. So therefore n equals 1. So we'll put that n back in there. And so we'll do 1 times our 6.626 times 10 to the negative 34th joule seconds. And then lambda we've already given you in meters, so 5.892 times 10 to the negative 7th meters. And so we're going to get 3.37 times 10 to the negative 19th joules. Okay? All right, so I want you to try. So the answer for this one, your energy on this one is going to be 4.84 times 10 to the negative 19th joules. Again, when you're dealing with nanometers for your wavelengths and you convert to meters, your energy for these should always be 10 to the negative 19th, okay, because of that order of magnitude. So why do we have this quantized energy? Well, this comes in to play with the fact that we've got these particle-like properties, okay? And so we've got electromagnetic radiation with particle-like properties in addition to the wave-like properties. So what if our electrons, which are particles, also have wave-like properties? And so the quantization comes as a consequence of having those wave-like properties. Because if you think of a wave, and if we think of a wavelength, it's the distance from peak to peak, or, we could also measure it trough to trough, right? I can't stop in the middle there, right? I can only go, through my wavelength. And so we get this quantization because of that. And so both EMR and electrons have a wave particle duality. And so we get this quantization because we've got this wave particle duality there. Now, one of the interesting things that comes about from these discrete energy levels and this quantization goes directly to our atomic spectra. So again, we're bouncing around between energy levels. And when we go down, we emit out a packet of light. And so what happens is when we have something like our gas discharge tubes and we turn that gas discharge tube on, that excites the electrons in that particular atom. And so they can jump up. They spend some time hanging out up there, and then they drop back down to the lower energy level. And what we see with our naked eye are these lines in the visible spectrum corresponding to the electrons making the transition back down from an excited energy level. So there's actually 3 different types of spectra that we can get: the ultraviolet, the visible, and the infrared. And so when we drop from that higher level down, we get these spectral lines. And so visible spectra, this one right here, these are corresponding from some transition of an energy level down to n equals 2. Okay, ultraviolet, higher energy level down to n equals 1, and infrared, higher level down to n equals 3. And this makes sense because remember, violet light is higher energy than red light is. And so our ultraviolet spectra comes from a transition all the way down to energy level 1, the biggest energy transition. Infrared, we're only going down to 3, which is a shorter energy transition. Now, these colors that I have on the visible spectra here, these are just there so that you recognize that this is in the visible, what we can see with our naked eye. The 3 to 2 transition is not necessarily a red line. The 7 to 2 transition is not necessarily a purple line or a violet line. It depends on what atom we're looking at and what actually is happening with the energy of those transitions. Okay, now each one of these gets a special name that they've been given, and so this just, the Lyman series is what the ultraviolet series has been named, the Balmer series is what the visible series has been named, and the Paschen series is what the infrared series has been named. Okay, and then that's on a circle there, so it's more like that Bohr model of the atom. Okay, now here when we think about the hydrogen spectrum, okay, again, the colors here doesn't mean that energy level 2 is blue or energy level 6 is red. The colors are just simply there because concentric circles can be hard to look at. And so these are colored just so that you can tell that, you know, the first circle is distinct from the second circle. And so when we look at the hydrogen spectrum, it's a 3 to 2 transition that gives us the red line. It's a 4 to 2 transition that gives us the blue-green line. And it's a 5 to 2 transition that gives us that violet line. All right. So this is a 3 down to 2 transition. This is a 4 down to 2 transition. And this is a 5 down to 2 transition. Okay. Now, how do we know this? Well, here's the thing. Hydrogen, as I've mentioned before, is super simple. It's got a single proton and a single electron. Well, sometimes it has a neutron, but most hydrogen is single proton. The key thing though is that we have that single electron. That single electron means is there's not other stuff in the atom for the electron to interact with and go all crazy. And so hydrogen is relatively predictable. It's easier for us to do calculations on hydrogen because we have the simplification of a single electron. The moment I put a second electron in there, even if it's in the same energy level, now the electrons are reacting with each other, and that starts to change things. But with hydrogen, we just have that one. And so we have this Rydberg equation. And so this Rydberg equation looks like this, where we've got 1 over lambda equals the Rydberg constant times 1 over n1 squared minus 1 over n2 squared. And so we can actually plug in the transitions in hydrogen and calculate the wavelengths that we see in hydrogen. So hydrogen's pretty cool. It makes it nice and easy. We know what the transitions that arise, or where we know what the transitions are that give rise to the various different colors and the lines that we see. Right? Again, hydrogen is also very predictable. Okay, and so I have this energy level for hydrogen. I get this negative 2.18 times 10 to the negative 18 joules over n squared, where n is just an integer 1, 2, 3, etc. So if it's energy level 1, the energy of hydrogen's first energy level is just negative 2.18 times 10 to the negative 18th. So hydrogen's simple. We can calculate things that go on within hydrogen because we can calculate the exact energy levels. And so here I have these, various different energy levels. So like, let's say I'm looking at a transition between energy level 2 and energy level 4. So let's say I'm going up to energy level 4. Well, how much energy would I need to make that transition to go up from 2 to 4? Well, because I know the energy levels of hydrogen, it's fairly simple. There's 2 ways I can do this. Okay, so we're going from 2 to 4 in hydrogen. Okay, so I can calculate my change in energy in 2 ways. I can do energy final minus energy initial. So this makes it super easy. Okay, and this is assuming I know what these are, right? So I do know this for hydrogen. So I take my negative 1.36 times 10 to the negative 19th, which was the energy assigned to energy level 4, minus negative 5.45 times 10 to the negative 19th. And what I get is I would need 4.09 times 10 to the negative 19th joules of energy to make that transition to go from energy level 2 up to energy level 4, which also means that if I'm up in energy level 4 and I drop down to energy level 2, I will emit 4.09 times 10 to the negative 19th joules. So if I'm doing 4 back down to 2, it would be negative 4.09. Okay, because if it takes 4.09 times 10 to the negative 19th joules to go up, we would have to emit that back out. Okay, but let's look at this 2 to 4 again. Okay, there's another equation that we can use for hydrogen. Okay, my delta E is that first energy level, that 2.18 times 10 to the negative 18th joules, minus 1 over n final squared, or what did I put minus? Times 1 over n final squared, minus 1 over n initial squared. Okay? So negative 2.18 times 10 to the negative 18th times 1 over 4 squared, because I'm going up to 4, so 4 is my final, minus 1 over 2 squared, because I'm starting from 2, 2 is my initial. And oh, look at this. I get the same amount of energy. Okay? So that's what happens with our quantized energy. And it is the quantization of the atom and these discrete energy levels that allow us to see our really cool atomic spectra. And so we can, with other detectors, see those lines in the infrared and the UV spectra. You have to have a special, detector technique to get those. But with our naked eye, with a gas discharge tube and a prism and something that splits it, we can see with our naked eye the visible spectrum. And so students here at Grossmont College, we actually do this lab. So if you are one of my students at Grossmont College, you will get to see this in lab. It's pretty cool. All right, so that's our quantized energy.